Okay, so here we go. Let's share the board. All right. So if you remember, an hour ago, not too long ago, what we're trying to achieve here, we're trying to achieve a simple CD circuit, right? And how we're going to do this, we'll first sketch out our Thevenin circuit. So this is my approach, the way I do it. So, excuse me. Check if I'm recording here. I am. So I'll sketch up a circuit. Oh, sorry. I will go green quickly. Simple Thevenin circuit. So you can have it, of course, any way really. So we're going to have our Thevenin voltage. So I'll say V Thevenin, the open circuit voltage across your Thevenin resistance, and we're going to have your load, right? Okay, so in this case, we're finding IL. This is in your textbook. That's one of the examples there, or one of the questions in the exercises. So of course, we're trying to find the resistance within the 5 ohms. So we know that this guy is going to be 5. So now we need to find the voltage drop, the open circuit voltage here, and we need to find the total Thevenin resistance. So normally we start by finding the Thevenin voltage. So what we do, we have to remove it and then open up our circuit. So okay, just bear with me. It's got a few things to sketch for. 7 ohm resistor. Here we've got 22 ohm and 8. Sorry, 10. And here we have an 8 ohm. Right? Open circuit. So the idea is that you want to get the voltage across here. So now what we have to basically do is now we're going to have to now, of course, once again now apply our voltage and current division. So where do we start, students? Can someone give me an indication? What's the first thing we do? Anyone? What is the first thing? So we need to, yes. Okay, no one. Okay. So looking at this, we have no current in the pot, so this guy and this guy is in series, right? So the first thing we have to do is take the 1810 is series, but this will be in parallel. So this guy and this guy just is 18 ohms. Then that and that will be in parallel. So it'll be 22 ohms and 18 will be equal to 22 times 18 and 18 plus 22. You should get the resistance of 9.9 ohms, right? So we can do this. That's in series because there's no current flowing through there. And then we basically have, if you look at it, we have one simple circuit again. So it's a circuit with 210 volts. We've got a 4. We've got a 7. And we've got all of that. That's a 9.9. So of course, obviously, we're trying to find the voltage. So we're going to use voltage division across here to find the voltage across the 9.9 resistor. Okay, so can someone work this out for me? what is my answer? Of course, we add all the resistances. It's fairly simple. 4 plus 7. What is my voltage across there? Across this piece over here. I'm waiting on you guys.
We're gonna have 99.
Yes. Yes.
47.
Great. 99. 47. I think it's 474, no?
474. Yes, sir.
Yeah. Great. So you've got the voltage there. Now, what we're looking at now, but then we still need our open circuit voltage, right? So that's the voltage across AB, but not the voltage across I'm just calling this AB, for instance, but we don't have it across that open side. So we still need to find the voltage over here, right? So I just quickly erase this again. Oh, don't erase it, just click it away. Delete. So once you have the voltage here, and this is now a series circuit, we're going to have to say we want the voltage across the 10 ohm resistor, right? So if you're going to do that, you're going to say it's the voltage this voltage here, so it's going to be 9.9474. That's a voltage across here, right? So the way, let me just resketch this part here. So we've got a voltage of 99. Of course, it's not a battery. I'm just simulating a battery. Then we've got 10, and we've got 8. So I find the voltage across the 10 ohm because that'll be exactly the same voltage over here. Open circuit voltage. It's 10 over 8 plus 10. So this is the voltage over the 10, and that'll give us, let me just work that out for you. 55.263. So we first have to find the voltage across this, and once we found this, then we can use now voltage division. So of course, this voltage includes this 22 ohm resistor, so the voltage across there. So we're again using voltage division to get there. Is there any alternative way you guys think for us to find the voltage? What way would you find the voltage? What do you do to find the voltage across this branch over here? Does anyone have any input there? Oh, calculate voltage. That's not understandable. What approach should you take?
We should also, in another approach, we find our current. I think.
Yes, that's good.
And then when we get there, we find our voltage.
Yes, so we can do current division, not something like that. Is that correct? So do you want to talk us through your approach, maybe? So we find it's a 9.9. There's 9.9, which is in parallel with. So I think another approach would be like this, maybe. We find the voltage drop across this over here. Maybe, I don't know. So we can find the current going through the 8 ohm and the 10. Something like this. So I'll have it as 22 and this 18 over here. Okay, so this is the voltage of now. So I'm basically going back here. You know, this is just another way of doing it. So that's a voltage drop across the 9.9 resistor. Then we find a current, right? Coming through the 18 ohm, because that is this over here is a 8 and a 10. I could say division is 8 and 10. So current is going to be 99.474 divided by 18. So if you get that, end up with a current of 5.5 to 5.5263. So of course that's the same current flowing through here. And then to find the voltage across the 10 ohm, I would say that value times 18. Oh, sorry, not 18, man. It's wrong. 5.5263 times 10. And I should get exactly the same answer. So remember, same current flowing through the 10 ohm and 8 ohm. Because they're in series, then I'll just say 5.523 times 10, and that'll give me 55 point. Oh, you get the idea. 55263. Sorry. Are we all happy with that? Maybe this is more intuitive than this one, right? Students, are we happy? Thank you. Okay, so then we have our open circuit voltage here, right? So this is going to be 55.263. Now we got to find our resistance. So I'm going to sketch up the circuit again. We're going to have, and this is where you're going to finally master this resistance, like that. This, that, 8, and that's all open. 4722, and we have 8 and a 10. So the way I do it, or they say looking in at the we should actually look this way now. We're adding up our R Thevenin. So when you're doing that, can someone please tell me what is my first? How are we going to add this up? So we're looking into that part there. Can someone work out? I'll give you guys 3 minutes to work out the total resistance here. I'll see if you guys get it. So you're working this way. So you're starting with this and you're moving this way.
Sir,
Did you get the answer? What's the Thevenin resistance? Fantastic, you got it. So how do we get there? So first step, this 2 is in series and that is in parallel with that, right? So we're going to say R11 and R, oh, it's going to be a few lines here. So it's R11, it's parallel with R22. That's going to give us 22 times 11. And that's going to give us 11 plus 22. What does that give us? 7.33.
7.33.
That's right. Then what we have next? Then we have this. This is now in series with this. So we're going to have a new resistance of 15.33 ohms because that and that's in series. This and this becomes in series. That's in parallel with this. Then this and that is in series. Going that way, then that. Then this will be in parallel. So then our Thevenin will be should be 15.33 times 10 over 10 plus 15.33. I hope this is right. Also did multiply by 10 there. And we should get 6,052 ohms. Take this back over here. Can we find the current? Oh, it's R Thevenin over here. You know, that's 5 ohms. 6,052. What do we get here? So maybe we're going back to our circuit. 5 plus 6,052. So there's our current there. Do we get the current? Fantastic, 5 amps. That's the correct answer. So, are there any questions with this particular approach? I'm going to give you guys now a small tutorial, basically. It's essentially to do with Thevenin again. This I like to see who are the big chiefs here. So do you remember the circuit here we just did now? That one? We're supposed to use Kirchhoff. When we use Kirchhoff, we use superposition. And now we're going to be using a Thevenin to solve the circuit. I like to see you guys do this approach. All right. I'll give you guys 5 minutes. Guys, Please practice. I mean, please work with me. Yeah. It's only for your benefit. I have a question for you quickly before we start, students. What is the voltage across? I'd like to ask you here. What is the voltage across here, here, and here? Can someone tell me quickly? Anyone? What? What kind of circuit is this? Hello? Pataso? Lindani?
Yes, sir. We just thinking a little bit.
So the voltage would be the same, right? Is it not so? Was it in parallel? Do you agree with me? The voltage across this branch must be equal to the same as this. It must be equal to the same as this. You understand? Does it make sense? Okay, so try and do, let's try and do, so we find the current through the 12 ohm resistor. Try and do Thevenin quickly. Do you guys manage? So did we manage? Brent, you're awfully quiet. Tristan. Okay. Right, let's have a look here. Where did I place my pen? Just give me a second. Hey. Okay, so first step, drop a circuit, right? So Thevenin circuit, and you've got your load, and we've got your R Thevenin, and we've got the what is this called again? The Thevenin voltage. So over here, we know that we want 12 ohms over here. So this is our focus. So first step, right? We open this guy up. So we open the guy up. We have 30 volts, 9 volts, 15, 9, and open. So we need to find the voltage drop across where, guys? We need to find the voltage drop. So do you agree with me? That you agree with me? Yes. Do you agree with me? This is a simple series circuit over here. That's over here. That's a series circuit, right? You agree? There's nothing happening on that side. Am I right?
That's correct.
Yes. So what will my current be here? So it's voltage over resistance. But what is my voltage? What happens if we have two voltages like that? If this is flowing against this, what do we do? We know at the bottom there's going to be a 15 and a 9. You agree with me? Right? But what is my voltage on top? If this opposes that one, can we say?
30 minus 9, sir.
Fantastic, fantastic. And what current do we get there?
21.
Yeah, 21 divided by the, I'm asking the current, so it's 0.875 amps. So now we have the current flowing through there. No, right. But the question is, we want to find the voltage, right? So what is that voltage across that open, the Thevenin voltage? Who can tell me? Who's smart here? So remember that the voltage must be the same, like I said, right? The voltage drop. So if I'm going to say 9 minus, and I'm looking at this circuit here, 0.875 times a current times resist. Oh wait, yeah, let me just quickly see, times 9. So I'm looking at this. I'm looking at the voltage drop across here now, right? So we have the 9, we've got current flowing there, and we have to subtract the voltage. So the voltage what I get here is 1.125 volts. If I look at this branch over here, the red one, I'll make this a green branch, green, and then the red branch. I should get the same voltage here. So it should be 30 minus 15 times, what's it? 0.875, right? So 30 minus 0.8 times, what's it? 15. No, what am I doing wrong here? For the first branch, my current times my resistance is 9 minus 0.8 times 9. And for the second is 2 times current times resistance. I should get the same voltage. Because it's the same voltage. I'm not sure what I did wrong here. Is it 30 volts? 30. Yeah, it looks right. I wonder if oh wait. My mistake is here, sorry. So for this branch, it should be plus, sorry, because we have to add the voltages. So that's 16.875. And if you do this on this side, you get exactly the same. So 30 minus 15 times 0.875. That's going to be 16.875 volts. You guys get that? So across this branch, we have to add that voltage and that voltage. However, at this point over here, coming in here, we're going to have to subtract, because we're going to subtract the 15. Are we all happy here? So there's two ways of getting the voltage across this thing. This is a very important thing, definitely coming in test and exam, this particular kind of thing. Are we all happy over here? Any questions with this? So that's 16.875. Can I get any questions with this? So I first found the voltage drop across here. So we have to essentially add them up. But if you're dealing with this branch, you're coming over here, you're going to have to subtract the voltage as we go that way. And in this case here, it's actually the total voltage across the branch. So obviously this is the more easy approach. Are we happy with this? So we found it's the voltage. We're basically adding a voltage here and a voltage here. Yes, Tristan.
Right from the start, right? Why do we minus 9 from 30 when we're working out the current?
9 and 30. I'm not with you. 9 and 30. Oh, you talk about the voltage. Remember that?
Yes.
That's impeding. It's impeding the flow of current. Kirchhoff's law.
Okay.
Are you not familiar with Kirchhoff's law?
No, this is my first electros lesson.
Oh, I see. So if you remember, like, let me just quickly copy and paste this thing. I can just get everyone on the same page here. Do you see this law? Do you see this thing over here? You got the voltage law. In any closed loop in a network, the algebraic sum of the voltage drops taken around the loop is equal to the resultant EMF. So we have something flowing. For instance, there's a circuit over here, and it's flowing this way. Can you see it's E1 minus E2? Are you familiar with that?
Okay, yeah.
Yeah, there we go.
Yeah, thanks.
So once you have that voltage over here, thank you for the question, man. I appreciate it. Let's find the Thevenin resistance. So remember, we remove all the sources now, right? So we have to, it looks like this. 15 and a 9, and we have to go this way. So this should be easy. What's my Thevenin resistance? So you guys burnt out.
5,625.
Students, any questions? Are we good? Thurston, Boulain, Mr. Neto. Yes. So that's Thevenin, guys. Okay. That's another approach that you're gonna have to practice. All right. Do you think you guys had enough, or can I go for Norton? Are you guys keen on seeing Norton? Okay, great. You can carry on. Just to, I guess, quickly show everyone. I would like to show everyone here. I'm going to open LP Spice now. Just to corroborate our answers over here. Show everyone exactly what's happening. Just click here, get our voltage source. You have another one. Have a resistor here, another resistor here, and another resistor here. Then we connect our stuff like that. That. that goes there. Spare me, I'm just trying to get this all right. So make sure my lines, don't know what happened here. So this is circuit simulation software I mentioned. Oh no, what did I do here? I should cut this out. Cut that, cut. Get another resistor in here. Oh. Oh. There is my wire again. Oh, stop this. Just give me a second. Zoom out, thank you. Right, just connecting my conductors here. Fantastic, right? Now we can classify our variables. So this guy was how many ohms? I think it was 30. This guy was 9 volts. The resistance here was, what's the resistance over here? You guys remember? 15. Let me have a look at this again. It's 15, 9, and 12. Okay. Right. Could simulate, run DC operating point in a DC analysis. And oh, never forget to ground the circuit. Just ground you anyway. It's perfectly fine. Simulate. We can run. There's our results. So let's have a look here. The current going through by V1 is minus 1.23. The current going through, or the current going through the resistance is that one there. I3, that's our answer. That's our answer. But look at our voltages over here at node 1. So nodes are these points over here. So it's a node here, another node, and another node. But you can what you can also do. Let me just make sure control. So keep control. Because it references my ground as 0 here. You guys see over there, it's the same voltage across there, there, and there. Are we happy with this? Just to prove to you. Students, are we all happy with that? Yes. So by the way, for me to measure this, I had to keep in control. Control over here. So, but here's I wanted to show you each and every voltage was the same. So over here, we're going to have to add the resistance of whereas this point here, we're going to have to subtract. It's a very important concept which. So I just wanted to show you guys that. Yes. Okay, guys, let's move on. Probably should just cut that out. And I'll paste it in the slides. Did we get 11,4 something? I'm not even sure what we got. No, we got 16. The Theorems voltage was 16, sorry. So of course it's not the same as this because different kind of setup over here. But the idea is that the current is flowing. If you take the current, what is the current by the way? Oh, the currents are all different. So obviously, you take the currents, you get it. The current here times that is the resistance. You should get the answer. Okay, so I'm going to go back to my slides quickly. I just want to paste. Just want to put this up under my. I just want to have it just similar you can run. I just want to snip to this so we all can have a look at exactly what's happening here. Oh, no. Yeah, there we go. All right, so it's very important to play around out these parts, especially if things are going to get confusing for you, so you can actually get the answers. Right, so let's get back to the lecture. Okay. So yes, guys, next approach is Norton. And with Norton, it's exactly the same as Thevenin, or not exactly, it's an extension rather, as they say here. Where is Norton from? I'm not too sure. But apparently it was developed by Maya and Edward Laurie Norton. And the idea here is it's exactly the same as Thevenin, but instead of using the open circuit and series open circuit voltage and series circuit, we're looking at what we're going to be looking at is basically a parallel circuit. So it achieves the same purpose, but whereas Norton will just focus on a parallel arrangement of here. So again, the idea is exactly the same. We're going to have a Norton circuit. We're going to have, instead of finding our open circuit voltage, we're going to find our short circuit current. And we're going to, R here is again the load. We take out the load. The short circuit, the branch, determine ISC, find the impedance. Now, luckily for you, you have experience finding the impedance, so the total resistance, which is exactly the same as Thevenin, and then we find the current. So let me show you an illustration. So if you remember this example here, it's exactly the same example we did with Thevenin, if you remember. The very first, open up for us now. The very first example. So the idea is I'm just showing you the same circuits using the same approaches. So we're going to go back to this one, problem 13 of this, it says, and we're going to try and solve it using good old Norton over here. Okay, so let's open this guy up. There we go. So of course it's going to say Thevenin here. So just to quickly recap, Thevenin, we had the green circuit over there. We started with that guy. What we did, we made an open circuit on the resistor what we want. We threw it over here in the green circuit. We found the open circuit voltage. Once we got that, and then we found our Thevenin resistance, which is exactly the same as a Thevenin as a Norton resistance. Okay, so let's quickly just do that and see. Okay, so now we're gonna just move along here. I'll just keep it just there. And then I'll just copy it from my slides over here. Oh no. Let me just have a look here. Let's paste this over here. Okay, so same circuit, it's actually the same. There's no difference. I think I need some more space here. Just here we go. Right. So I'll make this in green. I'll make this green as well. So in this case, like I said, we need a simple parallel circuit. Here we go. Here we have our current source, our I Norton, our R Norton, and our load resistance, also RL. And of course, here we can use current division, you know. That's the idea here. So of course here, 10 ohm is coming out, we're putting it here. So once we do this, so we're going to short this, right? Once we short this, this is how our circuit looks. Got 10 volts there. Got 8 ohms, 2 ohms. So I like to ask you guys, what happens to, if I short it, right? It's not that it's going to go, it's going to come like this. What happens to the 5 ohm resistor? What's going to happen here? Can you guys talk me through this? What is going to happen? Hey, what's going to happen to we short this? So something's going to change. Students are still there. You have an idea what's going to happen. So we're shorting this branch here. Becomes parallel with the 8 ohms. Are you sure about that? That's, I don't think it's a matter of parallel and series. I mean, if we short this, will there be any resistance? You know, maybe it will just, it's like nearly like an open circuit. Let's try and see what we get here actually. Let's see what we get here. I want to confirm something. Looking at the textbook here, I want to see something similar to this. For example, looks really similar to this. So we open this up. Yep. Let's have a look. This feel a bit okay. We short that guy. So this 2 is definitely in parallel. I agree with that. Let's hope, hopefully we can get the right answers here. So what we're going to sit with is R5 and 8 is 5 times 8, 5 plus 8. And of course, this would then be, remember, but what we're looking for is a current over here, right? So then we're going to have current is going to be equal to 10 volts, 2 plus whatever that value is. So what is that? That resistance? I'm hoping it's going to work out here. It's 5 times 8, 8 plus 5. So we should get 3,077 ohms. And of course, I'm just finding the total current within that piece over here. And the reason why I'm doing it is so then we can use current division instead. We could have done it with voltage division as well. 1,9697. I'm just always confused sometimes with the short circuit thing. But let's see what's going to work out here. Once you have the current, you find the current going through which branch? The 5 ohm. That'll be your short circuit current. because that's what we want. So we say 8 times, because that's in parallel, 1.9697 divided by 8 plus 5. I think John Bird's answer is what's the answer there? What's the answer? They have 5 amps for the short circuit current. That's why I'm a bit confused. But anyway, 697, 8 plus 5. So that's how I'm a bit confused here with this. A short circuit current feels a bit suspicious. 1 to 1 amps. As we short this might, but anyway, we have to have a look here. So this is my short circuit current here, right? Now this feels wrong to me because we're looking for an answer of 0.482. And that, if that is a short circuit or the Norton current, I doubt we're gonna get. But let's just quickly see. And if you look at your Thevenin resistance, let's have a look. Sorry, your Norton resistance. We'll remove this. Then we're gonna have a 2 and an 8. That 2 and an 8 is in parallel. And we do the same approach by looking in. Oh, it's the same as this here. 2. So that's maybe I'm writing 10. It's 2 times 8, 2 plus 8 plus 2. Oh, we had plus 5 there. It's plus, not plus 2, it's plus 5, sorry. So it's that 2 and then that one there. It should be the total. It should be exactly the same as before. And it should be 1, is it 1.6? What is it? So 6.6, sorry, 2 times 8, 2 plus 8 plus 5. 6.6, right? Are we all happy with it so far? Do we get the idea here? So I'm just going to recap quickly. I'm hoping it's all working out. Here we first found this 2 in parallel. And then we found the current going through this, the 8 ohm. But of course, we can use current division, and then we can find the current going through the 5 ohm, which is the Norton current, which is 1.212. So I've got the Norton resistance as well. So I'm hoping that now we need to find the current going through this, and we're going to use current division over here now. So I hope we're going to get the right answer. So now with John Bird, they kind of neglect the 5 ohm, and yeah, we'll see now. Hopefully it doesn't make a difference. Yeah, it shouldn't. Okay, it's fine. So you find the current going through that, you will get I10 is 1.212, right? Times 6.6, the one you don't want, over the total is 6.6 plus 10. Then you should get 0.48188795 amps. Students, do you get my approach for this? I just use Norton now. It's nearly the same. Are we happy with this? Should I re-explain? It's in parallel. You guys all okay with this? Can you guys hear me? Good. Thank you, Pauline. So, Pauline, back to the start. So we start with the parallel circuit here, right? Fine. The first step is we find this guy and this guy we find in in parallel, right? We short this, so we get that. You happy with that one? So once you find this one, 2 and 3,077 is of course in series, then we can find the current flowing here. So that's going to be I, right? So once you have I, remember that the current here, okay, so the new circuit, let me draw the new circuit now. So that's 2 ohms. This is going to be now 3,077. So we found a current of 1.9697. But remember, this is in parallel, right? So what happens over here, we open this guy up. I've done this a few times before. And this is going to be the 5 and the 8. But remember, we are concerned with the current going to the 5 ohm resistor. So then we use current division. And then we can find the current going through that line over here. And then you use current division, and then we get your I Norton or ISC. And we put it is 1.212. Pulling, are you following so far? Right?
Yes, sir.
Great. Next step is exactly the same as the Thevenin. So we're gonna remove all the sources. Like this. What was it again? It's 8 and 2, and remember that 5. And we've shorted this now, looks like that. And then we do exactly the same thing. So we look this way, looking into to the sector. 2 and 8 is in parallel. We get that plus 5. That'll be in series with that total. We get 6.6. That's our R Norton. Remember your R Norton, R Thevenin is exactly the same value. Very important. You plug it back here, and then looking at our green circuit, we just basically use current division, and of course we choose the one we don't want, which is 6.6, because we consider a 10 ohm resistor. Use current division, and we can get the answer. Is it clear to everyone now? Okay. I hope you guys got some knowledge from that. Guys, I think what's best now, I think I want to call it, but I just want to show you guys, because I mean it's really been a heavy session, which is fantastic. Let me just open up. I want you guys to go to chapter 2 in your Electrotech 2 textbook. I was advanced kyk now, so please make sure you get those copies. And I want to show you. So, and you're in chapter 15 of John Bird. I hope you guys can see this, right? Make sure if I open the subsections in the chapter, this is one of my favorite electrical technology books. Go to DC circuit theory to see all this. Kirchhoff's superposition, Thevenin, constant current source, Norton's. Okay, let's explain what it is. There is a multitude of examples for you guys to do here. And if you go to revision test 4, see here, they're asking you here to do Kirchhoff laws, superposition, Thevenin, and Norton. The test would be something similar to, you have to know all your theorems, so make sure you practice this. If you don't know the answers for circuits, use LT Spice. That's why I made you guys aware of it. So I hope you guys enjoyed today's lecture. It's been rough. The next chapter won't be so rough. It'll be a nice chapter. I think this is one of the harder chapters in Electrotech 2. And enjoy the rest of the day. I'll see you soon and keep in touch. Thank you very much.